Hi, good morning. This is Dr. Jagadish. I'll be taking biochemistry for you, and I am really excited to meet you all through Medico. In this session, we are going to cover previous year questions of INI-CET and NEET-PG. So I'm really excited for you. We'll learn together. And first of all, I want to welcome you all to Medico app, which is doing a fantastic job. So today in this live session, I'll be covering the previous year questions of NEET PG and INI-CET. So let's go chapter wise. So let me start my session now. Okay, so we are looking at the first question. Which of the following is true regarding non-competitive inhibition? Okay, so here the answer is C. Let's see how we got that answer. First, non-competitive inhibition. There are three types of inhibition, enzyme inhibition: competitive, non-competitive, and something called mixed. So when it comes to non-competitive inhibition, the inhibitor binds either the free enzyme or enzyme substrate complex. So what is this? So usually when you write a reaction, enzyme combines with a substrate to form enzyme substrate complex, which will form a product. Okay. So this non-competitive inhibitor binds either the free enzyme or the enzyme substrate complex, but it binds to a site other than the active site of the enzyme. So when this happens, the Km will not change. The Km will remain the same, as you can see from the graph where I am working now. However, the Vmax will decrease. So with the inhibitor, the Vmax will decrease. So that's about it. So in case of non-competitive inhibition, there won't be any change in Km. There will be a change in Vmax, which is actually a decrease. So what is Km? Km is nothing but Michel's constant. Michel's constant is nothing but the substrate's concentration at which the velocity is half the maximum. So that's Km. So what happens in competitive inhibition? Competitive inhibition, the inhibitor structurally resembles a substrate. It's a structural analog. So it binds to the active site of the enzyme. So in this case, Km will increase. Km will increase. However, the Vmax will remain unchanged. There won't be any change in Vmax. So this is about competitive inhibition. Okay. So there's something called mixed inhibition, which is nothing but it displays the features of both competitive and non-competitive inhibition. So we're having heard this. So the answer is C. So in non-competitive inhibition, there won't be any change in Km, but the Vmax will decrease. So the answer is C. Okay. Let's go to the next question. Okay. So this is actually a problem-based question. So in a reaction, substrate is available in a concentration that is 1000 times the Km value of the enzyme. After 9 minutes of the reaction, 1% of the substrate is converted to product, which is around 12 microgram per ml. If the concentration of the enzyme is changed to 1/3 of its original concentration, that is, you're going to reduce the concentration of the enzyme by 1/3. And you're going to double the concentration, how much time it will take to convert the substrate to the same amount of product, is 12 microgram per liter. So for this, we need to understand few things to answer this question. First, what is Michel's-Menten equation? Michel's-Menten equation is an equation which is there to know about enzyme kinetics. So what is Michel's-Menten equation? The velocity is equal to Vmax, which is the maximum velocity, into substrate concentration divided by Km, which is Michel's constant, plus substrate concentration. So the rate of the reaction does not change with increase in the substrate concentration above a threshold. That is, if you increase the substrate concentration, the rate of the reaction will increase to a certain point. After that, it will become plateau. Why it becomes plateaued? Because all of the active sites are occupied by the substrate at that concentration. So beyond, if in this point, after becoming a plateau, even if you add substrate, it is not going to change the rate of the reaction because it's already plateaued, it's already saturated. Okay, so this is what it is. So at what point it will happen? It will happen roughly at the twice the Km. So what is Km? I already told you. Km is a concentration of the substrate at which the velocity is half the maximum. So this, if you double it, this is the point at which the enzyme will get plateau. That is, almost all the active sites of the enzyme will get saturated. So in this case, to start with, the substrate concentration is already 1000 times the km. It's already 1000 times the km. That means the substrate is present in very high concentration. That means all the active sites are already saturated. In this state, so in this condition, the rate of the enzyme depends only on one factor, that is enzyme concentration. Okay, so this is very important. Substrate is already present at 1000 times the km. It is in the supersaturating conditions. So at that state, the rate of the reaction is completely dependent on the concentration of the enzyme. So, but what happened now is they have reduced the enzyme concentration by 1/3. And they doubled the concentration of the substrate. It's already 1000 times, they almost doubled it. Okay, so what will happen? So I said the rate of this reaction depends only on the enzyme concentration. Now we have reduced the enzyme concentration by 1/3. So what will do is it will prolong the rate of the reaction by 3 times to produce the same amount of the product. That is, normally it takes 9 minutes in the supersaturating conditions. Now you reduce the enzyme by 1/3, so it will take 3 times. So 9 times 9 minutes into 3, that is 27 minutes. So when you alter the conditions like this, the enzyme will take 27 minutes to produce the same amount of product. So that's the answer. So the answer is C, 27 minutes. Okay, that is, the enzyme concentration is reduced by 1/3. So the rate of the reaction increases by 3. So the rate of the reaction is, the original rate of the reaction is 9 minutes. So 9 into 3, which is nothing but 27 minutes. So under these conditions, the same enzyme will require 27 minutes to produce the same amount of product, that is 12 microgram per ml. Okay. Comment on the following statements regarding the mechanism of an enzyme action. So they are saying that they are given 4 statements. They are asking us to say whether each statement is true or false. So first statement, Gibbs free energy is lowered. Second, the transition state stability is reduced. Third, specificity is based on the complementarity of the active site of the enzyme and the substrate. D, there is some conformational change at the active site. So for this, you have to know this graph. Okay, if you see here, there is a graph with course of the reaction on the x-axis and the free energy on the y-axis. Now there are 2 colored curves. One is green color, one is red color. And the red color is the uncatalyzed reaction. The green color is the enzyme catalyzed reaction. Okay, so what is the reaction we are looking at? We are looking at one important enzyme of glycolysis. First step of glycolysis, glucose is converted to glucose 6-phosphate. During this process, ATP is utilized to form ADP. Okay, this is done by the enzyme called hexokinase. Okay, so what happens to this reaction in the absence of an enzyme? That is what you see in the red color. What happens to this reaction in the presence of the enzyme? That is what you see in the green color. Okay, see, to start with, these are the reactants, glucose and ATP. The glucose and ATP will react together to form a transition state. That is an intermediate state. That is a transition state. That is what you see here. It reaches a transition state where the free energy is increased, and then this will be converted to a product. What is our product? Glucose 6-phosphate and ADP. Okay, the energy difference between the initial state and the transition state. The energy difference between the initial state and the transition state is called as activation energy. Okay, if you see carefully, the activation energy for the uncatalyzed reaction is high, whereas the activation energy for the reaction catalyzed by an enzyme is low. So what enzyme actually does is enzyme is actually lowering the activation energy, thereby favoring the production of a product, formation of a product. But if you see the free energy change, see the reactants react, goes to the transition state and comes down to form a product. If you see the change in free energy between the initial state and the final state, there is no change in free energy between the reaction catalyzed by an enzyme and a reaction not catalyzed by an enzyme. The free energy of the reaction remains constant. Okay, one. So first, activation energy is lowered. Second, the free energy of the reaction remains constant. Third, if you see this transition state, the enzyme, what it does is it helps to stabilize the transition state, so that you will find so that the enzyme will be able to form the product. The free energy gets lowered, the activation energy gets lowered, and the product is formed. So the transition state is stabilized here. One. So this is what is three things that you should keep in mind from this graph. One, activation energy is lowered in the presence of an enzyme. The free energy of the reaction remains constant. There is no change in free energy of the reaction. Plus, the transition state is stabilized. So when this is an enzyme, what you see here is an enzyme. It has an active site. It has an active site. The substrate binds to the active site. So upon binding of the substrate, the enzyme undergoes a change in conformation, especially the shape will change. Some amount of conformational change will happen to form enzyme substrate complex. After that, the enzyme is converted to, substrate is converted to products. The products will leave the active site of the enzyme. So the binding of the substrate to enzyme, not all substrates can bind to any enzyme. Okay, only the substrate which is specific to that site can bind it. So the complementarity is based on the complementarity of the substrate and the active site determine the specificity of the reaction. Then upon binding, there is some slight conformational changes at the active site. So with this, we'll try to find out the answer for this. The Gibbs free energy is lower. No, that is not false, because the free energy of the reaction remains the same. Stability of the transition state is reduced. No, that is also false. The enzyme will try to stabilize the transition state. The specificity depends upon the complementarity of the active site of the enzyme and the substrate. That is true, because only that substrate can bind to the enzyme. D, the conformational changes occurs in the active site upon binding of substrate. That is also true. So false, false, true, true. So answer is B. So that's how we got the answer for this question. So I hope that was clear. So let me go to the next question. Kcat divided by Km. There is a ratio of Kcat. There is Kcat Km ratio is a measure of what? Okay, let us see what it is. So what is Kcat? Kcat is nothing but a catalytic constant. So what does it say? It is an index of product formation from the substrate. That is, number of substrate molecules converted to a product by a single enzyme per unit of time. That is, how many molecules of the substrate are converted to products by a single enzyme. This micromole per minute. Under which condition? Under the condition that the enzyme is fully saturated with substrate. Okay, so when you have an enzyme in the presence of saturating concentration of the substrate, how much product is formed from the substrate, or how many molecules of the substrate are converted to a product? That is called Kcat. So what does Kcat tell you? Higher the Kcat, higher the enzyme efficiency. So when an enzyme's Kcat is higher, the enzyme is efficient. Okay, it is also known as turnover number. Okay, so that's about Kcat. What is Km, which we already discussed? Km is the Michaelis constant. It's a substrate concentration at which the velocity is half the maximum. What is Km will tell you? Km is actually inversely proportional to affinity of the enzyme towards the substrate. Higher the Km, lower the affinity. Okay, so now we know what is Kcat. Kcat is a catalytic constant, which is the efficiency of the enzyme, and we know Km, which is the Michaelis constant. This ratio is an index of catalytic efficiency or enzyme specificity. Okay, that's the answer. Kcat by Km ratio is an index of catalytic efficiency. Answer is A. So that's about this question. Kcat by Km is a measure of enzyme efficiency. Okay. Selenocysteine is present in all the following enzymes except. Okay. Selenocysteine, they're asking, is not present in which enzyme? Okay. Selenocysteine has some special feature. It is a 21st amino acid present in the active site of enzymes that catalyze redox reactions. It's a 21st amino acid. Okay. So, what are those enzymes? Glutathione peroxidase, thioredoxin reductase, and deiodinase, which is present in thyroid gland. Okay, these are the enzymes which contain selenocysteine. Glutathione peroxidase, thioredoxin reductase, and deiodinase. So, what are the functions of this enzyme? These two enzymes, glutathione peroxidase and thioredoxin reductase, are antioxidant enzymes. That is, these enzymes are responsible for preventing the damage caused by reactive oxygen species. What is the function of deiodinase? Deiodinase will convert T4 to T3. T3 is metabolically active. Deiodinase is present in blood, it's present in the target tissues, it's also present in the thyroid gland. And there are many types of deiodinases. All deiodinases contain selenocysteine. Okay. So with this, we'll try to answer this question. So it is present in glutathione peroxidase, it is present in thioredoxin reductase, it is present in deiodinase. It is not present in thyroid peroxidase. So what's the function of this thyroid peroxidase? Thyroid peroxidase is responsible for organification of iodide, the formation of T3 and T4 in the thyroid gland and the colloid. That is about the thyroid peroxidase. Okay. So that's about the enzymes. So enzymes basically lower the activation energy, one. Second, they stabilize the transition state. Then the complementary of the enzyme determines the specificity of the substrate and enzyme binding. One, second, and then free energy of the reaction remains unaltered. So it won't change the equilibrium, but it will speed the reaction. So that's about the enzymes. And Km is called Michaelis constant. It's nothing but the substrate concentration at which the velocity is half the maximal velocity. Okay, let's go to this question. A child is presented with multiple episodes of loose stools and he is managed with ORS. Identify the transporter which is essential for correcting dehydration with the help of ORS. Okay, so if you see here, ORS contains various components. So if you see here, it contains sodium chloride, potassium chloride, sodium citrate, then dextrose. So if somebody is dehydrated, okay, we give them ORS. Why? To correct the dehydration, right? So in dehydration, water is lost. So when water is lost, some of the electrolytes are lost. Importantly, sodium and chloride are lost. Okay. So in order to rehydrate it, we can just give water, right? So why do we give ORS, which also contains dextrose? What's the analogy of having dextrose in the ORS? Fine. So if you try to find out the answer for that, you will find out the answer for this question. We will try to find out the answer for that. So absorption of carbohydrates into the blood circulation, that is absorption of dietary carbohydrates into the blood circulation across the intestine. So that's what this slide will show you. Okay. So this is an intestinal cell. This is the brush border, and this is the AP. This is the basolateral aspect. That is, this is the basolateral aspect. So after appropriate digestion, glucose, all complex carbohydrates will be converted to simpler monosaccharides, just glucose, fructose, and galactose. Okay. So this glucose and galactose, especially glucose, is absorbed into the introsite. It's taken up into the introsite through this transporter called SGLT1. It's also called as sodium glucose transporter. See, I'm just teaching you how carbohydrates are absorbed in the intestine. We'll come to ORS later. So this SGLT1 will try to absorb glucose into the introsite. How this functions? This is a co-transporter. So whenever one glucose molecule enters, sodium also will enter. So sodium and glucose enters into the enterocyte. Once the glucose is inside the enterocyte, it comes out of the enterocyte through GLUT2, which is present on the basolateral aspect. GLUT2 transport, glucose transporter 2. It's a facilitated diffusion transporter. So once the sodium comes inside, the sodium is exchanged with potassium through this transporter called sodium potassium ATPase. So for this transporter to function, that is for sodium glucose transporter 1 to function, we need sodium potassium ATPase. So that's why this is an excellent example of secondary active transport mechanism. Okay. So sodium, the intracellular concentration of the sodium has to be maintained. Only the sodium can come inside. So that is done by this transporter called, that is done by this channel called sodium potassium ATPase, which is an ATP dependent transporter. Fructose, very simple. It comes through GLUT5 and then goes out through GLUT2. That's it. Okay. So with this, we came to know SGLT1 is present on the apical aspect, where it absorbs glucose along with sodium. Once inside the enterocyte, it's taken out of the enterocyte through GLUT2, which is a basolateral glucose transporter 1. And sodium inside the enterocyte is maintained by the sodium potassium ATPase. With this knowledge, we'll go to now our case, diarrhea. So patients with diarrhea are usually treated with ORS. As I already told you, ORS contains sodium chloride, potassium chloride, sodium citrate, then dextrose. So we are going to replenish, the primary aim is to replenish water and sodium. Then what's the concept of having dextrose here? That's the reason because of this transporter. See here, this is what we discussed in the last SGLT1. This is the transporter. So glucose comes inside, as I told you earlier. For every one glucose molecule that comes inside, 2 molecules of sodium also comes inside. The ORS contains dextrose, it's nothing but glucose. ORS contains sodium chloride, potassium chloride, etc. So that's sodium. So you take ORS powder, mix it with water. So there is water, sodium, glucose in the gut. So glucose is absorbed. Whenever glucose is absorbed, 2 molecules of sodium is also absorbed. So what happens? The sodium concentration in the bloodstream increases. Whereas in the lumen, it will be low because everything is coming inside. So this will create an osmotic pull. This will create an osmotic difference between the bloodstream and the luminal side of the bowel. So this pulls water. So this pulls all water molecules into the blood. So that's how water is replenished. So if you don't have sodium, if you don't take glucose, the sodium will come inside, but the amount of sodium that's going to come inside is going to be very low. So that's the concept of having glucose in the ORS powder. The glucose, when it comes inside, for every 1 molecule of glucose, 2 sodium comes inside. So that is going to create an osmotic difference. It is going to create a pull a lot of water molecules inside. That is also called a solvent drag. So with this, we know that the transporter, which is very important for ORS to work, is sodium glucose transporter 1. Okay, so that's about it. The answer is A, sodium glucose transporter 1. So that's the concept of having glucose in the ORS powder. That's why they say when somebody is having diarrhea, to drink home-based ORS is nothing but salt as well as sugar. Salt contains sodium, sugar contains glucose. So if you just drink salt and water, it is not going to get absorbed because SGLT1 will not function. Sodium will enter, but it won't be that much higher enough to replenish the water. So they will still be dehydrated. Okay. So then there's few words about the glucose transporters. Okay, glucose transporters are various types. There are almost around 14 types. I'll just tell you about a few important types. GLUT1 is present in RBCs and brain, responsible for the basal glucose uptake. GLUT2, we already saw, it's present in the intestine on the basolateral aspect. It's also present in the pancreatic beta cells, liver, and kidney. GLUT3 is present in the neurons. GLUT4, very, very important. It's an insulin-dependent glucose transporter. So where you will see that? You will see only in 3 tissues: adipose tissue, heart, and muscle. GLUT5, just we saw, it's intestine responsible for the absorption of fructose. So that's about it. Okay. Transparency of corneal endothelium is maintained by, okay, they're given you 4 compounds: keratin sulfate, heparin sulfate, chondroitin sulfate, hyaluronic acid. What are these substrates actually? These substrates are nothing but glycosaminoglycans. Okay, among this, which is responsible for maintaining the transparency of cornea? That's the question. Okay, and the answer is B, keratin sulfate. We'll see how. See, first, glycosaminoglycans are also called as mucopolysaccharides. Okay, it is a heteropolysaccharide. Okay, that is, it's made up of more than one different sugar units. Okay, so what is actually it's made up of? It is an unbranched molecule made up of repeating units of 2 things. What are the 2 things? Uronic acid and amino sugar. Okay, so this glycosaminoglycans are synthesized in the endoplasmic reticulum and Golgi apparatus. So what are the various glycosaminoglycans we know? These are the various glycosaminoglycans: hyaluronic acid, chondroitin sulfate, keratin sulfate, dermatin sulfate, heparin, and heparin sulfate. Okay, so each glycosaminoglycans which I have listed now vary in their tissue distribution, vary in their components, and vary in their functions. Okay, for example, hyaluronic acid is present in HSV. Okay, synovial fluid and vitreous humor. What it is made up of? I said it is made up of repeating units of uronic acid and amino sugar. Okay, so it is made up of glucuronic acid, which is a uronic acid, and amino sugar, glucosamine, amino sugar, glucosamine. Where is it found? It is found in the ground substance of the extracellular matrix. These are the functions. It is also responsible for cell migration. Okay, chondroitin sulfate, as the name suggests, is present in cartilage. It is present in glucuronic acid. It is made up of glucuronic acid and N-acetyl galactosamine. So chondroitin sulfate is present in the cartilage, hence it helps in the lubrication of the joint space. Keratin sulfate, it is present in the cornea. It is present in the cornea. Okay. Keratin sulfate is made up of galactose and N-acetyl glucosamine. So there's one difference here. It is not made up of uronic acid. It is made up of galactose and N-acetyl glucosamine. So this is responsible for maintaining the transparency of the cornea. Dermatin sulfate, name suggests it's present in skin. It's made up of iduronic acid, N-acetyl galactosamine. It's responsible for maintaining skin elasticity. Heparin, which is present in mast cells, lungs, liver, and skin. It's made up of glucuronic acid or iduronic acid and glucosamine. Its main function is anticoagulant, very well known. Heparin sulfate is found in the basement membrane. It is made up of glucuronic acid and glucosamine. It is responsible for cell-to-cell communication. So these are the various glycosaminoglycans, where it is seen, what it is made up of, and what are their functions. Coming back to our question, which glycosaminoglycan is responsible for maintaining the transparency of the cornea? So it is keratin sulfate. So the answer is keratin sulfate.